Thank you very much. I'd like to thank the organizers for the invitation to speak to you today. And I will apologize for the change in the schedule, but we'll try to get through most of what I plan to talk to you about novel influenza viruses. So I'm going to see if I'm able to change slides. Doesn't look like I am. So I'm just wondering if I can request that the slides be advanced. Yes, thank you. Influenza A viruses occur in a wide range of species, and influenza A viruses and only influenza A viruses have a number of different subtypes. So the hemagglutinin and neuraminidase, which are the surface glycoproteins, have come in a number of different subtypes. And on this slide, schematically, you see 18 subtypes of influenza A hemagglutinins, of which 16 are present in waterfowl and shorebirds. Next slide, please. And the neuraminidase come in many different subtypes as well, of which there are now 11 known subtypes, 9 of which are present in waterfowl and shorebirds. Next slide, please. So the natural cycle of avian influenza viruses is in waterfowl and shorebirds, from which they spill over occasionally into domestic birds that include chickens and turkeys, and from there into mammals, including pigs and humans. Next slide, please. So the history, if we look back over the last century, we've had 4 influenza pandemics, indicated up at the top of this figure: H10n3 in Spanish flu pandemic, the H10n2 arrival in 1957, H3n2 viruses in 1968, and then the pandemic 2009 virus in 2009. Now, 2 of these viruses, we believe actually, one of them at least, the 2009, was directly introduced from a virus that was circulating in pigs. And all the other viruses are avian introductions into humans. And I've already pointed out to you what the reservoir is. And in between these years, when a novel virus is introduced into humans, there's antigenic drift, where viruses continuously change as a result of mutations. Next slide, please. So the sources of novel influenza viruses that are confirmed are avian species and pigs. And hypothetically, bats and other animal species could also be sources for influenza infections in humans. I say it's hypothetical because we haven't identified any discrete examples of infections from bats, but it's theoretically possible. Next slide, please. So most of our focus is on avian species and pigs. Next slide, please. Yes, there we go. So avian influenza viruses in their natural reservoir, and waterfowl and shorebirds really do not cause any clinical signs. But when they transfer into domestic poultry, they can cause disease. And that disease can be either referred to as low pathogenicity or high pathogenicity. With low pathogenic infections, there's very mild disease, but yet there might be decreased egg production. Whereas highly pathogenic avian influenza used to be called fowl plague, and this causes a multi-system hemorrhagic infection with severe disease, rapid death, and high mortality. We'll skip the next 2 slides, just go through the next 2. One more, and the next one. So those ones that I skipped through were pictures of highly pathogenic avian influenza. So we used to think that avian influenza viruses would only infect people if they reassorted with the previously circulating human influenza virus, because that had been the case with the 1957 and 1968 pandemic strains. However, on this table, you will see a long list of documented infections where people have been infected directly by an avian influenza virus without undergoing reassortment with the previously circulating human strain. And the ones that are boxed in colors are the 3 subtypes that we are most concerned about. So we're most concerned about H5 viruses, H7n9 viruses, and H9n2 viruses. And you'll see that one of the boxes actually includes H5 and H7, and the next box includes H5n6 and H5n8. Next slide, please. So just looking over this past year, we haven't seen seasonal influenza activity in most of the world, although there have been pockets of it in the tropics. But we've certainly had a lot of animal influenza virus circulation, and we've had several different viruses that have caused zoonotic infections. And summarized here on this slide are zoonotic infections coming from bird species or from swine. And so we've summarized here H5n1, H5n6, H9n2, H10n3. All these infections have occurred in humans from birds. And then in the three below, the three bottom ones are swine influenza viruses. Next slide, please. So this is a figure that was generated by the OFFLU program, which is OIE and the FAO at their research on animal influenza surveillance. And it summarizes with a picture of a map of the world and a little graph below that indicates recent H5, H7, and H9 activity in birds. So that is actually the source from which we have these novel infections in humans. Next slide, please. So with H5 viruses, they first came to our attention back in 1997 with the first cases from Hong Kong. And then in 2004, there was a reemergence of them. In this period of this past year, there have been 23 cases. But overall, we've had many cases of H5N1, N6, N8, and of course H5N1 is now up to 863 human infections reported. Now, over the years, the viruses in birds have diversified into several genetically and antigenically distinguishable clades. And so now we actually follow them in specific clades to see which ones are circulating. Next slide, please. H7 viruses came to the forefront in 2013 with the emergence of an H7N9 virus in China. Previously, there had been a limited outbreak of H7N7 virus infections in Germany and the Netherlands, but for several years we had cases of H7N9 infections in humans in China. But there have been no human infections recently of H7N9 in China. Next slide, please. This is the result of their vaccination program targeting H5 and H7 viruses infections in birds. Now, H9N2 viruses, unlike the H5 viruses, are not highly pathogenic. They cause very minimal disease in birds, and they cause mild disease in humans. We do continue to see sporadic cases of H9N2 infections, and 7 were reported from China and 1 in Cambodia in this past year. Very often these cases tend to be mild and people recover well from them. And none of these viruses that I've talked about so far have acquired the ability to transmit efficiently from person to person. Next slide, please. And there was a recent H10n3 infection that was identified as well. And this virus was quite unique compared to the previous H10 infection that had been reported some years ago from China. What is common to many of these infections, viruses that infect humans, is that the cassette of internal protein genes are often derived from H9N2 viruses. Next slide, please. So now I'd like to switch to talking a little bit about the swine influenza viruses. So influenza A viruses in pigs that are circulating around the world come in 2 subtypes, H1 and H3. And what you have on the left is a phylogenetic tree of the H1 viruses with the map below it. And on the right-hand side are swine influenza A H3 viruses and a map below that. And you can see that there's quite a bit of genetic heterogeneity amongst the viruses that are circulating around the world. And now sporadically, we have introductions from these hosts into humans. Next slide, please. When these infections occur in humans, we put the initial V, which is variant, to distinguish them from the H10n3 and H10n3 viruses that cause seasonal influenza. So the variant, or V, it designates them as a swine origin virus. And so we've had a number of cases of H1 variant viruses in Europe, Asia, and USA in this past year, and 2 cases of H3N2 variant from Canada and the USA, all of whom have recovered with mild illness. Next slide, please. So in summary, we've had a lot of zoonotic influenza, even though we haven't had very much seasonal influenza this past year, both from avian species and from pigs. Next slide, please. So why do we worry about these? We worry about them because when a novel influenza virus is introduced into humans, and if the general population has little or no immunity against it, if the virus has the ability to replicate and cause disease and spread efficiently from person to person, we would end up with a pandemic. And that's historically how the pandemics have arisen. So we are always interested in knowing about the appearance of novel influenza viruses and zoonotic infections, and in characterizing them to understand whether they have the ability to or have the potential to cause a pandemic. Next slide, please. So what are the determinants? As I said in the previous slide, the population has to be susceptible. So this is measured, you can do this by doing serosurveys. You can collect blood samples from each decade of life, and you could test to see whether the general population has antibodies against that specific virus. And this was done in 2009, and it demonstrated that people under the age of 50 were largely seronegative and were susceptible to infection with the 2009 pandemic virus. Next slide, please. So the factors, the viral factors that are determinants of the pandemic potential are, many of those factors reside in the hemagglutinin gene, which is the surface protein of the influenza virus that is responsible for virus attachment. And it is involved in determining the host range and tropism of infection, infectivity and virulence, transmissibility, and antigenicity. Next slide, please. So this is these are 2 figures from papers that came out very much at the same time, looking at the receptor binding specificity and the importance of receptor binding specificity and tropism, and the distribution of those receptors that would allow an H5 virus to bind. So H5, which are avian influenza viruses, preferentially bind alpha-2,3 linked sialic acids, while human influenza viruses preferentially bind alpha-2,6 sialic acids. So the reason this makes a difference is because the alpha-2,6 linked sialic acids are present throughout our respiratory tree, and alpha-2,3 linked sialic acids are largely present in the lower respiratory tract. Next slide, please. But there are other characteristics in addition to the receptor binding and tropism that include the pH sensitivity and thermostability, which are also determined by the hemagglutinin and neuraminidase. Next slide, please. So there are several traits that are associated with airborne transmissibility in humans. Now, this is important because it meets the 3rd criterion that a virus has to meet in order to cause a pandemic. It has to be able to transmit efficiently from person to person through sustained chains of transmission. So what we have here are the characteristics of viruses that are associated with airborne transmissibility, summarized on this slide. Next slide, please. So there are all these characteristics. You can hit the button again, please. We'll fill up the whole slide. Next. One more, please. So what do we do about knowing about these viruses when they transmit? As I showed you, There are lots of viruses that are circulating in the animal reservoirs and in animal species. Periodically, they can cross into humans. So how do we decide, and how should one decide that a certain virus poses a greater pandemic threat than another? So the Centers for Disease Control in the United States and the WHO have come up with risk assessment tools where they take into consideration a number of different virus properties, host properties, and ecology and epidemiology that are outlined on this slide. And all of this is taken into consideration in order to determine what the risk is to humans. Next slide, please. Next. Yep. So the equivalent tool developed by the WHO, which is quite similar to the CDC tool, is called TIPRA, which is a tool for influenza pandemic risk assessment. And here, these are the characteristics, and they're weighted. And technical experts provide point estimates and their confidence scores in order to develop confidence coefficient scores. Next slide, please. Next slide, please. Next. Yes, and so here's an example of how all of this information is taken into consideration. But of course, the TIPRA tool is designed for use when an influenza virus has caused at least one human infection. So it doesn't actually apply when it's a theoretical construct. But the idea is that you will take all of this information into consideration to make a risk assessment. Next. So these are the types of technical experts that contribute to the risk analysis. Next slide, please. All right, so now we know the viruses that are in circulation. We know what some of the characteristics of viruses that can cross the species barrier are. We know some of the host characteristics that might contribute to a pandemic potential. And we've got risk assessment tools where we could take all that information and try to figure out what risk they pose. So what do we do about protecting the population? So we've got antiviral drugs, which generally speaking should work against avian influenza viruses and swine influenza viruses. And the second and more important, the sort of backbone of our protection strategy is to use vaccines. So our current vaccine strategy is to make a library of candidate vaccine viruses that are based on viruses that have crossed the species barrier or represent a pandemic threat. And so the WHO committees that meet to discuss human influenza seasonal vaccine composition also discuss zoonotic vaccines. And so we meet regularly to review the data from OIE and FAO and OFLU and other academic colleagues around the world to determine when to update vaccines. Next slide, please. What we really need are approaches to elicit more broadly cross-reactive immunity so that it covers viruses within the subtype better. And this might be done by oil and water adjuvants, by using whole virion vaccines, by selecting different viruses for the development of the CVVs, or combining vaccine platforms. Next slide, please. But the ultimate goal would be to have a universal influenza vaccine that would cover viruses, all influenza A viruses, or potentially all influenza viruses. And there are many different targets that are being evaluated. There was a lot of attention to H10n3 vaccines, and H10n3 and head vaccines are still under consideration. People are interested in the neuraminidase, in M2, in combinations of vaccines that include HA with NP and M1, as well as T-cell-based protection. Next slide, please. So in the interim, of course, although we are in the midst of a coronavirus pandemic, and we've learned certainly that influenza is not the only virus with pandemic potential, if you ask most people, they still consider influenza to represent a potential pandemic threat. So we cannot afford to lose track of what's going on with influenza in humans as well as in the animal species around us. And so there's a lot that we can learn and apply from the success of the COVID-19 vaccines. And we hope that the sad events of the last 2 years will actually energize people to think about the potential for zoonotic transfer of viruses and the need to prepare for these events. Next slide, please. And this is my last slide, and it's to acknowledge the WHO Global Influenza Surveillance and Response System, the OIE FAO Network of Expertise on Animal Influenza, and the Global Initiative on Sharing All Influenza Data, which is GISAID. So with that, I will stop and hope we have time for maybe just a few questions.
Thank you very much, Prof. Kanta. We do have time for some questions. And I wonder if I can sort of start off by asking you, first of all, as you mentioned, flu cases have dropped significantly over the past couple of years. I'm just wondering what your predictions are for the coming Northern Hemisphere season. How quickly do you think we'll see a resurgence, and do you know which subtypes we might expect to see?
Right, so that's a loaded question because most influenza virologists know better than to predict. So what I will say is that people have asked if influenza is gone. We haven't seen it for 2 years for sure, but I don't think it really was ever completely gone. So when we look at the global data, there was influenza circulation in tropical regions in Asia, India, Bangladesh, as well as in parts of Africa. So Togo and Cote d'Ivoire all had some influenza activity. China's had quite a bit of influenza B Victoria activity. So if you ask me, I would say that we really do think influenza will be back. Now, all of the seasonal influenza viruses have gone through a very severe genetic bottleneck. We don't know which of them is going to come out at the other end and how transmissible or how fit they'll be. So it might not happen in the very first season, but we've also had 2 years of no circulation of influenza, and vaccine uptake has been poor. So we are also setting the population up for potential for a more severe season if the virus returns. So sitting in Australia, I can tell you that we've had some influenza isolates, not from the community in Australia, but from returned travelers. And Australia, until recently, had a mandatory hotel quarantine system where returned travelers had to quarantine for 14 days. So we actually picked up even family outbreaks within travelers, but they never seeded the community. Now, Australia is opening its borders soon, and hotel quarantine is not going to be mandatory. So we may actually see some seeding of viruses in the community. So the only thing that I will predict is that we may not see influenza B Yamagata, because it's been a while since anyone had seen an isolated B Yamagata. So that's the only thing that I'm actually comfortable predicting. Otherwise, I'd say we'll see influenza. It may not be in the correct season. Of course, in Singapore, you don't have the same seasonality that we do in temperate Australia.
Great, thank you very much. Yeah, sorry to put you on the spot. To sort of ask another question from you, was saying about sort of translating some of what has been learnt from COVID over to flu. I'm just wondering, what specific parts do you think might be useful? For example, do you think if we do get a big influenza outbreak, may masks and social distancing be worthwhile bringing back for that? Or are there aspects of influenza surveillance in hospitals particularly which perhaps could be ported over from COVID? What do you think would be most important for us to retain?
Yeah, so I think that you're absolutely right. I think that one of the things that we've learned from COVID, learned the hard way, is that there was a delayed recognition and acceptance in many parts of the medical and public health community in parts of the world that airborne transmission was a reality. I think that's really changed. It's been slow to come, but it's changed our thinking. And we've learned much more about ventilation and about personal protective gear that works for airborne transmissible pathogens. So I think all of this is really going to make a difference when we think about flu and when flu returns. So we certainly have nosocomial outbreaks of influenza in many places. We also have outbreaks in aged care. So maybe some of what we've learned about ventilation and about use of air purifiers and so on might make a difference. The other area where I think we might learn a lot and take some lessons from COVID-19 is the use of novel vaccine platforms. They have been really exciting. We now have to see if those platforms work for influenza. And the third thing I would say is that the development of new vaccines for COVID-19 required public-private partnerships and a very different way of vaccine development where things weren't sequential, they happened in parallel. So I think the acceleration of the development process might also translate to influenza.
Okay. Thank you very much. Very interesting. And yeah, I think that's all we have time for today, unfortunately. But thank you very much to Prof. Kanta and to all of our speakers today. And thank you for listening to this symposium.